Hi all, this is my video number 11. So in this video I'll talk well, this is quite short video. So I'll talk on the notes on E, important note on E. And note on E. So what do we know about E? E is 2.7 something, right? 2.7 something, which means it's between 3 and 2, between 2 and 3. How can we prove this? That's things. Means, how can we prove that E, not that value because that's accurate, E in between 2 and 3? So how to do that? First, we look at the power series. If you look at the power series of 1 plus x to the n, I think we know this. This is from, we got this is 1 plus nx plus n minus 1 over n factorial, over 2 factorial x2 plus n minus 1 n minus 2 over 2 factorial 3 factorial x3 x cubed and so on, plus up to x to the n. The power series of x plus 1 plus x. Now, if we substitute x with 1 over n. So what, just substitute there, x with 1 over n. So what we have is that 1 plus 1 over n to the n, this is equal, just substitute everything there, x with 1 over n. So we have 1 plus, here x is 1 over n, so n cancel out, what left is only 1 plus. The same thing here. Alright, so we have n minus 1 over 2 factorial, and x is 1 over n, so we have 1 over n squared. The same thing with that, so we have n minus 1, n minus 2 over 3 factorial, x cubed, we have 1 over n cubed, and so on until we have the last one. We have basically this is n minus 1, n minus 2 up to, we reduce until 1, so which means you have n factorial, and here you have 1, 2, 3 factorial, 4 factorial, 5 factorial, and later on you got n factorial. So what you got at the end, you have n factorial over n factorial, 1 over n to the n. Alright, so if you simplify this, if you look at here, let me write this part here. If you factor out n, so what we have, take out those n, so what we have is n factorial, n squared. You have 1 minus 1 over n, correct? 1 minus 1 over n, because you take out those n. And then we have outside there, we have 1 over n squared, and we have over 2 factorial, those things. So you can cancel out this. What left is 1 minus 1 over n over 2 factorial. You can do the same for here, for that case, and the next case, and the next case, the next term and the next term. For this part here, for example, you can factor out those n, each of those terms in the expression. So what we have is n cubed Okay, so because this is n, this is n, this is n, so you have n cubed there. So what left is the first term here, you have 1 minus 1 over n. The second term you have 1 minus 2 over n, and then we have 1 over n cubed. You have 3 factorial there, and then you can cancel out this. What left is that, and then you can continue with all those things until the last term. So what you have, this will give you 1, this is the first term, your second term is 1, the third terms you have this. Okay, I can write this as a 1 over 2 factorial, 1 minus 1 over n, okay, plus, and we have those 1 over 3 factorial, 1 minus 1 over n, 1 minus 2 over n, alright, and you can proceed this thing up to you have 1 over, you can see here 2 factorial, 3 factorial, 4 factorial, and so on. So basically you have up to 1 over n factorial, and inside there, so we have 1 minus 1 over n, 1 minus 1 over n, alright, and then you can have 1 minus 2 over n next term. So basically we can just 1 minus n minus 1 over n up to that. Okay, and then obviously consider each of these terms. Consider each of those terms. Okay, so what we have 1 over n, look at carefully, 1 over n is greater than 1 over n plus 1, correct? Because n plus 1 greater than n, if you invert that, you get 1 over, so this is greater than that. So since that one is greater than that, so because we want to consider inside here, we have 1 minus. So we have 1 minus 1 over n. Okay, because 1 over n is bigger than that. So 1 minus what you left is pretty big, right? So basically this is less than 1 minus 1 over n plus 1. This is a simple algebra. Okay, you just look at this from 0 to 1, 0 to 1. Here, first term, say, let's say we have term here. So 1 minus that part here, consider quite big as compared to this one is quite bigger. 1 minus those part here, what left is pretty much smaller. Alright, so based on that, so each of those terms, okay, we can write, so we can write that as this is less than, so I need those terms, so less than, using that fact, okay, using that fact. So those I can write, this is less than 1 plus 1 plus, we have 1 over 2 factorial, 1 over 2 factorial. Here, we have 1 minus 1 over n plus 1. Plus, here we have 1 over 3 factorial. And that, for each n, we change to n plus 1. So this is still satisfy our inequality here. So we have 1 minus 1 over n plus 1. And 1 minus 2 over n plus 1. Alright, and then you can proceed this up to last term here. We have 1 over n factorial, 1 minus 1 over n plus 1, and so on. 1 minus n minus 1 over n plus 1. Okay, so this is up to n terms. Up to n terms. I can add up one more terms so that we have up to n plus 1 terms. Means we add up one more terms, so which means your right hand side which should be bigger than your left hand side. right hand side, I mean, for this case, for example, this is the right hand side of the previous term. Okay, this is the right hand side of the previous term. So means that the right hand side of this is the term after this. So we have this less than. Okay, so we have 1 plus 1, that all these are the same. So I have 1 over 2 factorial 1 minus n plus 1 plus 1 over 3 factorial 1 minus 1 n plus 1 1 minus 2 over n plus 1. I hope you can see those things. Alright, plus we have this term here, 1 over n factorial 1 minus 1 over n plus 1 up to 1 minus n minus 1 over n plus 1, and we add up one more terms, I put it here, 1 over n plus 1 factorial, then we have 1 minus 1 over n plus 1, and then this all the way up to 1 minus, we add one more terms, so n over n plus 1. Okay, so why do we do this? Because we want to find the power series of 1 plus 1 over n plus 1. That's the purpose, because we want to find what is, now we have 1 plus x. We want to add one more. Okay, so what we have now, this is basically the power series of, this is equal to exactly the same if you look at here. Alright, exactly the same. You have here 1 plus 1 when n equal to that, so 1 plus 1 and so on, so when we change to that. So we have all those things except that we have one more extra term, n plus 1. Alright, the same thing with n, we have extra term n plus 1. So which means we have here, all these things is equal to 1 plus 1 over n plus 1 to the n plus 1. Okay, obviously in this case we have 1 plus something, so which means our sequence is increasing. So therefore the sequence is increasing. Is increasing. All right, now furthermore we have, since we have 1 minus 1 over n up to 1 minus k over n, this is less than 1. This is obvious, right? This is obvious because this is for k from 1 to up to n minus 1. So look at k less than n, yeah, k less than n. So you look at each of these terms. This term here is less than 1 because 1 minus something less than 1, so you got less than 1, as well as that less than 1. So we multiply all those things, we still got less than 1, right? So since we have those terms is less than 1, so which means we have 1 plus 1 over n factorial. 1 plus 1 over n to the power of n. This term here. Now look at each of those terms. All right, this is less than 1, less than 1, less than 1, everything. So what we have is that this is just less than. We have 1 plus 1. The rest is less than. Yeah. Look at again. Or you can look at from here. Okay. This is for n plus 1. This is for n. Alright, this is for n plus 1. This is for n. So for n, you can. This is less than 1. This is less than 1. This is less than 1. So everything inside that. This is less than 1. Everything that less than 1. everything then less than 1. So basically you have less than 1 plus 1, 2 over 2 factorial plus 1 over 3 factorial and so on. So you have here, this is less than 1 over 2 factorial plus 1 over 3 factorial and so on up to 1 over n factorial. And of course n factorial is greater than 2 to n, so you put it down there, so it should be less than. So this is less than 1 plus 1 plus 1 over 2 plus 1 over 2 to 2 and so on plus 1 over 2 1 and minus 1. So you can see here this is 1 plus 1 is 2, this less than 1. In fact, from here you can see this is less than 1. Alright, so which is altogether you got 1 plus 1, you got 2, this is less than 1, so basically more than 2 but less than 3. So therefore we have E is in between 2 and 3, because this is 1 plus 1 definitely greater than 2, because we have 2, and then you have another extra terms there which is less than 1, so definitely it cannot go bigger than 3. So therefore E between 2 and 3. So what the conclusion from that is, what we can see is that since we have E between 3 and 3, so which means our sequence that we have discussed just now is bounded. And we know that first we have shown the sequence increasing, alright, and then the second part just now we show that the sequence is bounded, which means the sequence is converging, which means we have a convergent sequence or convergent sequence. The convergent sequence means that the sequence must have a limit. There's a limit, which means if we take a limit of our sequence, n goes to infinity, our sequence is 1 over n over to the power of n. This gives you E. Alright? So therefore we have the limit of that sequence is equal to E. So if you consider any form of this, you'll got E. Any form of this, 1 plus 1 over n plus 1 to the n plus 1, 1 plus 1 over n minus 1 to the n minus 1. If you show that, it will go to, you got E. So let's look at on those things. All right. So let's consider knots. All right. So let x be positive number. Okay. So x be any positive, let's say, real number, and we take x, this x, the greatest integer less than n, the greatest integer less than n. Greatest integer less than n. Yeah. Normally I put in your notes we use that notation, those bracket. In some book they use that symbol. Yeah. The greatest integer less than n. If you use this symbol, this is the smallest integer less than n. Can also. Now in this case we use that symbol, which means it's greater integer less than n. What does it mean? So it means that if you have 2.7, for example, so greatest integer less than n, this is your n, so is equal to what? 2, right? Greatest integer less than n, so it should be 2. All right. Now, so which means in this case, greatest integer less than n, so which means our n is equal to those. I use notation in your notes. Therefore we have our x is in between n and n plus 1. And we have, all right, so 1 plus 1 over n plus 1 to the n. So just look at those things. We just replace those n. You put those as a denominator. So it will be the inequality will opposite. So if I put it 1 over, so you have 1 over n plus 1, that will be less than equal to 1 over x less than 1 over n. So we use this fact. From that you have those. So this give you less than, and we have add those 1 plus 1 over x to the n to the x less than equal to 1 plus 1 over n to n plus 1. This is correct. Okay, but we know that the limit n goes to infinity 1 plus 1 over n plus 1 to the n, right? This is just e that we have shown earlier, and this is just the same as limit n goes to infinity 1 plus 1 over n plus 1. Because if you take logically, if 1 plus 1 over n to n equal to e, you just add 1 terms n plus 1, whereas n goes to infinity plus 1. That give no difference. Alright, so it still got the same answer. So therefore from here, we got this thing equal to e, this thing equal to e, we take a limit, alright, left and right equal to e. Automatically in the middle one you got e. You can use the what you call sandwich theorem, right? So therefore the limit as x goes to infinity 1 plus 1 over x to the x, this is equal to e for all positive integer n. Now for all positive integer x. Okay, now look at a couple of example how to use this. I only have one example only. Okay, only one example. Oh, I'm running out of papers. Just a minute. Look at the example. Now bear in mind that we have limits n goes to infinity 1 plus 1 over n to the n. This is e. Now look at the example. Given that if limit n goes to infinity 1 plus 1 over n equal to e, show that limit n goes to infinity 1 plus 1 over n plus 1 to the n equal to limit n goes to infinity 1 plus 1 over n plus 1. This is equal to e. Yeah. if you realize, this is the term that we have discussed just now, that we give equal to E. So now we're going to show Y is equal to E. Alright? So we prove this. Now first, for that, we have n plus 1. Now in this case here, 1 over n. So just the same as if I take n plus 1, we consider other symbol. Let's say let m equal to n plus 1. So if I do this, then what we have, yeah, the limits n goes to infinity, 1 plus 1 over n plus 1 to the n. Alright, this is just equal to, if n goes to infinity, look at this one, n goes to infinity, which means m also goes to infinity, because m just has n plus 1. Alright, so which means I can write this as a limit m goes to infinity, because we replace everything with m there. So we have 1 over m, n plus 1 is m, and your n is m minus 1. Alright, then you can use the index rule here. So this is equal to limit m to infinity, 1 plus 1 over m, and you have one more term minus there, so which means you have divide by 1 plus 1 over m. This one you have m. This part here, as m goes to infinity, 1 plus 1 over m exactly the same as this. Alright, so which means you have E. That one you have E. Divide by, for this term here, you take a limit, 1 plus 1 over m, m goes to infinity, that part is 0, what left is only 1. So you got E. On the other hand, so I hope you can understand this. On the other hand, we're going to show the second part here. That. Okay? We're going to show this. We do the same with m equal to n plus 1. If you substitute into that, so I put here also, or n, and also we have limits n goes to infinity, 1 plus 1 over n, n plus 1. Alright, so this is just equal to, we have limit n goes to infinity, 1 plus 1 over n to the n. Okay, just use a index properties, yeah, rule of index, multiply by 1 plus 1 over n. So in this case, it's pretty obvious that this part is exactly given in the question at the beginning of the question, if that equal to E. So which is, this part is E. Whereas for this case, if you take a limit n goes to infinity, you got that one is 0. What left is only 1. So you multiply by 1. So basically this multiply by 1. So that give you E. So we have shown that those equal to E. Now, can you extend a little bit? Let me, just to play around with it. Alright, can you show that the limit n goes to infinity, 1 plus 1 over n plus 1, n plus, let's say 2, if you want. Show that this is also equal to E. It's not difficult, you can do it and play around with it. You can play around with it. Alright, so I think that's enough for this video, because in the next part I'm going to talk a bit different than just an E, Alright, we'll talk on the supremum and infimum, limit superior and limit inferior, and so on. Alright, so for the time being, what I've done, what I've discussed within about half an hour, is that just important notes on E, the number E itself, which is 2.71 something, 2.71 something. Then we have shown that E is between 2 and 3, and also we have the, I would say, a formula for the limit to obtain E. So by using that, you can solve many problems that related to E. One of the example that I gave in the last part of my video. So with that, I thank you. See you in the next video. Bye bye.